you two champions, welcome to Dhurandhar Series, and in today's class we are going to do the one-shot revision of one of the most important physical chemistry chapter, that is chapter number 2, Electrochemistry. So in this video I will be covering each and every concept in the simplest possible way so that you can understand everything and can prepare well for this chapter. So if you have already studied this chapter or you haven't started yet, please watch the entire video so that if you have already studied, you will revise it. If you haven't, you will complete this chapter. That I can guarantee you. So let's get started and see what we have in today's class. So first of all, we'll discuss the topics of this chapter. So first we'll talk about electrochemical cells. How many types of cells are there and what are they? Next, we'll talk about galvanic cell in detail, Nernst equation in detail, conductance of electrolytic solutions, then what is an electrolytic cell, what is battery, what is fuel cell, and lastly, we'll talk about a very common phenomena, that is corrosion. Okay, so first let's start with electrochemical cell. See, electrochemical cells are of two types. One is galvanic cell, one is electrolytic cell. Now, galvanic cell converts chemical energy to electrical energy. Okay, means there happens some chemical reactions, and when the chemical reactions happen, chemical energy is there, and this energy is getting converted to electrical energy. In case of electrolytic cell, what happens? You provide the electrical energy, and due to this electrical energy, certain chemical reactions takes place or some chemical energy is produced. Okay, so electrical to chemical is electrolytic cell, chemical to electrical is your galvanic cell. I hope this is clear. Now let's move to galvanic cell in detail. So what we will study in galvanic cell, first we will talk about Daniell cell. Okay, this is, I'll tell one example of galvanic cell. Okay, this is an example of galvanic cell. Then we'll talk about what is electrode potential, what is cell potential and how to write a cell notation, measurement of electrode potential and inert electrodes. Okay, so first let us start with Daniell cell. So so first of all, I'll go back and discuss some more thing. You should understand that in a galvanic cell, okay, I told you that chemical energy is converted to electrical energy, right? Now, in this chemical energy comes from where? This comes from chemical reactions, definitely. Now, what type of chemical reactions do we consider in this particular type of reactions? So, we consider here redox reactions, okay? Redox reactions are the type of chemical reactions from which the chemical energy gets converted to electrical energy. Now, redox reaction, I hope all of you know, when you have reduction plus oxidation simultaneously. Okay, in a galvanic cell we have two containers. Okay, on one side there is oxidation and on the other side we have reduction. So now let's talk about Daniell cell in detail. Okay, so in Daniell cell you find that one side we have zinc rod and the electrolyte that is present here is zinc sulfate. Okay, an electrolyte of zinc is taken, and on the other side you see a copper rod and the electrolyte that is taken here is copper sulfate. Okay, now what happens? The two containers are connected with a U-shaped tube called as salt bridge. Okay, now what happens? See, understand the mechanism of this Daniell cell. So what happens? Zinc is a one which can undergo oxidation. So zinc undergoes oxidation to give you Zn2 plus 2 electron. So what comes out here? You get Zn2 plus here, okay, and 2 electrons are released here. Now these electrons move from the external circuit and come here. Okay, these electrons come on this electrode. Now in this electrolyte, what is there? Copper 2 plus is there. So copper 2 plus gets or go towards the electrode, gain these electrons and gets converted to copper. So copper 2 plus 2 electron gives you copper. This is the reduction half cell and this is the oxidation half cell. So what you have to understand, when I add these two reactions, the overall reaction of this Daniell cell is zinc plus copper 2 plus gives Zn2 plus copper. Okay. Okay, now what we have here, that this is the direction of flow of electrons. Current will flow in the opposite direction of that, right? So zinc is, if electrons are flowing in this direction, current will flow in the other direction, right? Now something that is important that you can remember through one mnemonics, that is load. You should always understand that on the left side, okay, there is oxidation on the left hand side. This is the left hand side, and here there is always oxidation, and oxidation always takes place on the anode. Okay, now if you see here, this Zn comes out and electrons are built up here, right? So the charge of this anode will be what? Negative. Okay, so this is what you need to remember. So Daniell cell works like this, or any galvanic cell works like this. We have two components. One is oxidation half cell, one is reduction half cell. On the oxidation half cell, oxidation takes place, and on the electrode, the electrons are produced. These electrons move through the external circuit and reaches the reduction half cell. The ions present in the electrolyte gain these electrons and gets converted to solid. Okay, now we will talk about what is electrode potential. The potential difference between the electrode and the electrolyte is called as electrode potential. Okay, so you can see here that you have an electrode and you have one electrolyte. Okay, you have one electrode and you have electrolyte. Now as we see in the zinc one, what happens? The Zn2 plus ions came out and electrons were collected on the electrode. So there is a potential difference between this, right? Between these electrons and the ions, there's a potential difference created. The electrode is negatively charged and around it there is positively charged ions around it. So due to this, I can say the potential difference that is generated here, that is called as your electrode potential, and that is present for both oxidation potential and also in the reduction half cell there will be reduction potential. So the potential difference between the electrode and the electrolyte is called as electrode potential. Now we will talk about some more things about this electrode potential. So let's see this one. See, when the concentration of all the species involved in the half cell is unity, okay, that means all the species means you have the electrolyte. If its concentration is 1 molar, then the electrode potential is known as standard electrode potential. Okay, you need to know what is electrode potential and what is standard electrode potential. Now, if in this particular diagram, if I have the one second, if the concentration of this electrolyte is 1 molar, okay, then and the temperature is the room temperature, then whatever potential that is generated here, that is called as your standard electrode potential. Got it? Now let's move forward. According to IUPAC convention, the standard reduction potentials are now called as standard electrode potential. Okay, so as I told you, there are two types of potential. On the oxidation half cell you will get oxidation potential, on the reduction half cell you will get reduction potential. But IUPAC has made a common term that every electrode potential should be represented in the terms of reduction potential. Now I'll give you an example. What is oxidation potential and what is reduction potential? See here, as we have seen that zinc, right? Zinc is undergoing oxidation. So what is the oxidation potential of zinc? How will you write? Zn2 Zn2 plus. Okay, and what is the reduction potential of copper? Because copper is undergoing reduction, so Cu2 plus 2 Cu. This is the reduction potential and this is the oxidation potential. Now what will happen? Now what will happen is the IUPAC has said that all the potential should be written in the terms of reduction potential. This is already in the terms of reduction. You can see Cu2 plus 2 Cu0, that is the reduction one, but this is a oxidation one. So suppose this value is X. Now if I want to write it in the term of reduction potential, then I will write E naught of Zn2 plus 2 Zn. This is how it has to be written, and the value of this one is minus X volt. Okay, getting this one, minus X volt. Okay, next we will talk about, does there exist a potential difference between two electrodes, and as soon as the switch is it switches in the on position, the electrons flow from negative electrode to the positive electrode. So if you see two containers I have, right? I have two containers here in the galvanic cell. You have, so there is some potential difference here and there is some potential difference here. Due to this two potential difference, the electrons start moving from the negative electrode to the positive electrode. Okay, the direction of current flow is opposite to that of the electron flow, that we know in the physics also. Now let's understand what is the cell potential. You understood what is electrode potential. Electrode potential is the potential difference generated between the electrode and the electrolyte around it. What is cell potential? Cell potential is the difference between the potential gradient between two halves of the cell, means oxidation half cell and reduction half cell. So you can see the potential difference between the two electrodes of the galvanic cell is called as the cell potential and is measured in volts. Okay, now it is called as the cell electromotive force or EMF of the cell when no current is drawn through the cell. Okay, if there is no current drawn through the cell, then we call it as the cell electromotive force. Now always remember that, see, when you calculate the cell potential, okay, E naught of the cell, it is written like this, E naught, this represents what? Standard conditions. What is standard conditions? That we have 1 molar of electrolyte and the room temperature, the potential is measured. So E naught of the cell is equal to E naught of cathode, okay, E naught of cathode minus E naught of anode. Okay, E naught of the cell is equal to E naught of cathode minus E naught of anode. Clear? Now let's talk about the cell potential and cell notation. So how to write the cell notation? See, every time you will not be drawing this much big diagram to represent the cell, right? There is a shortcut way or a more conventional way to represent the cell. So that is what we will study in the part of cell notation. So how to start? You have to start from the zinc rod. Okay, so I'll start first. Sorry, you will start from this electrolyte. Okay, you will start from this electrolyte. Okay, so I'll just draw like this. One second, we will start from this one. I'll draw this salt bridge is there with us, let's assume. Okay, so first start with this rod. So what is zinc here? Okay, its physical state is solid. This is in contact with Zn2 plus. Okay, and that is in the aqueous state. Now this one is in connection with the salt bridge. So draw the salt bridge like this. Then you have copper 2 plus. Okay, and that is again in the aqueous state, and that is in contact with copper, which is in the solid state. Okay, so this is the proper, I can say, equation or how we can represent the cell notation. Sometimes when the concentration of this one is different, the concentration of the ion is also mentioned in the Nernst in the cell notation. Clear? Okay, now we will discuss about how do we measure the electrode potential. Okay, so I told you that there is a potential difference between this Zn and the electrolyte. There's a potential difference here, but how do we measure that? So to measure that, there is something we use called as SHE, that is standard hydrogen electrode. Now standard hydrogen electrode looks like this. You can see here it has one you can see one platinum wire is there, and there is a platinum plate, and on this the hydrogen gas is adsorbed. Okay, now this hydrogen gas undergoes reaction, and this is an electrolyte, or this I can say is a electrolyte of hydrogen containing H plus ions. Now what happens, this particular cell or this particular setup has a electrode potential considered to be 0 volt. Okay, now what we have seen that I have in how does this galvanic cell works, understand here. So this is very important. You have this one and you have one more cell, one more half, and here we have two containers, and this is something which measures the potential difference between two. This is x and suppose this is y. This gives you the value of x minus y, right? Now what we'll do is, suppose I want to measure the zinc potential difference or zinc electrode potential. So one side I will connect zinc and other side I'll connect hydrogen. Okay, so I'll get again, so let this one be zinc and let this one be x, or the hydrogen electrode. So I'll get the value of these two, x minus y is suppose z, and we have already considered that x, the hydrogen electrode potential, is 0 volt. That means what I can say, y is equal to minus z, right? So like this we can calculate by taking this hydrogen electrode as a reference electrode. We can calculate the potential, electrode potential for any element. So I'll show you how the setup goes. First let us understand the structure of the standard hydrogen electrode. So it consists of a platinum electrode coated with a platinum black. Okay, you have a platinum wire and then you have a platinum black. The electrode is dipped in an acidic solution and pure hydrogen gas is bubbled through it. Okay, the pressure of the hydrogen gas is 1 bar and the concentration of the hydrogen ion is 1 molar. Okay, so pressure is 1 bar and concentration is 1 molar. Its potential is assumed to be 0. So we have, this is how we represent the hydrogen electrode. We have platinum wire, then we have H2 gas, and here this is H plus. Okay, we have H2 gas and then we have H plus. Now what is the reaction of this one? You have H plus plus 1 electron, that gives you H2. Okay, so half H2. Clear? Okay, now let's understand that how we can measure the electrode potential of any particular metal or any particular element using the hydrogen electrode. So one side you have to take this hydrogen electrode and another side you have to take that element whose electrode potential you want to measure. Okay, so you can see this side I have the entire hydrogen electrode and this side I have zinc electrode. So now this value is x and this value which I want to measure, this value is y. So now this potential difference, okay, this voltmeter will give me the difference between x and y. Okay, and since I have assumed that x is equal to 0, so whatever difference comes, that will be equal to y. Okay, now if I want to write the cell notation for this one, Pt, H2 and H plus. So anode part is written first, then you have Zn2 plus and Zn. Okay, now the value is minus 0.76. Okay, corresponding to the standard electrode potential of the half cell reaction. So you can see here that this value, according to this one, x minus y, okay, so this value and this value gave me a value of 0.76. So this Y value will be equal to minus 0.76. Okay, so that is what is the reduction potential of zinc. That is how we can calculate. So whichever element you want to measure, position that with hydrogen electrode, and whatever difference you get, that will be the value. Okay, now let's talk about the inert electrodes. So inert electrodes do not participate in the reaction, but they only provide the surface for oxidation or reduction. Examples of inert electrodes are platinum and gold electrodes. Okay, now we'll move to what is Nernst equation. Okay, so I told you that if the galvanic cell is under standard conditions, then E naught of the cell is equal to E naught of cathode minus anode. The standard conditions means the concentration of the electrolyte should be 1 molar and the temperature should be at the room temperature. But what if the condition are non-standard? Means what if the concentration is not 1 molar? So in that case, to find the electrode, to find the cell potential, we use one equation called as Nernst equation. Okay, so now let's see, Nernst equation can be used for two things, that is for electrode and for the cell. So when you calculate the electrode potential only, at that time also you have standard electrode potential, and if the concentration is not 1 molar, then it will be under non-standard conditions, and similarly you can calculate for the cell also. So first let us understand the equation for the electrode which is under non-standard conditions. Means you have a electrode, then you have this electrolyte. Okay, one second, you have this electrolyte, and here some potential difference is generated. Okay, and this electrolyte concentration is not equal to 1 molar. Okay, it is not equal to 1 molar. So here the equation is like this: m n plus n electrons gives you m. Okay, next we have E is equal to E naught minus RT by NF log of product by reactant, you should write. So m, that is on the product side, divided by the reactant. Now what will happen? Again, E is equal to E naught minus RT. So for the solid one, the concentration is taken as 1 molar. Okay, so this becomes 1. So I have 1 by m n plus. Now what I can do, I'll just convert this one to log. So 2.303 RT by log NF. Okay, this ln is converted to log by multiplying it with 2.30 RT. Now if you just solve all this 2.303 RT by F, then the final value we get is 0.0591 by N. So E is equal to E naught minus 0.0591 N log of this concentration of the ion. Okay, now the Nernst equation can be used for the cell also. Suppose I have this particular cell. Okay, then what will be its Nernst equation? So Nernst equation will be E of the cell is equal to E naught of the cell. How will you calculate E naught of the cell? E naught will be equal to E naught minus cathode, E naught of cathode minus E naught of anode, minus RT by 2F. Here 2, okay, one more thing here I want to mention. N is what? N is the number of electrons involved. Okay, similarly here if you see, nickel is getting converted to Ni2 plus, number of electrons involved is 2. Similarly Ag plus is getting converted to Ag, 1 electron is there, 2 Ag means 2 electron will be there. So here also, that is why N value is 2. Ln of product concentration divided by reactant concentration, Ni2 plus divided by Ag plus, then its square is taken. Now what will happen? E of the cell is equal to E naught of the cell minus 0.059 N. So you have this ln can be converted to 2.303 log. So you will have 2.303 into R into T by F. So if you solve this, you will get N log of Ni2 plus divided by Ag plus square. So that is the final equation of the Nernst equation. You should be very careful here that if any stoichiometric coefficient is there, its power must be considered. Okay. Okay, now we'll talk about Nernst equation and equilibrium constant. So see, at equilibrium, what happens? The E of the cell becomes 0. Okay, if E of the cell is 0, what is my Nernst equation? E of the cell is equal to E naught of the cell minus 0.0591 by N log of product concentration divided by reactant concentration. Only ions has to be considered here. Now if this one, E of the cell is equal to 0, then what I'll get? E naught of the cell will be equal to 0.059 by N log of, now at equilibrium this ratio is the equilibrium constant. So 0.059 by N log of K. Okay. Now let's talk about Gibbs free energy. Delta G is equal to minus NF E naught of the cell, and delta G is equal to minus 2.303 RT log of K. Okay. These two equations are done. Now we'll talk about the conductance of electrolytes. See, in this particular electrochemistry, our electrical conductors, the electricity is conducted by electrolytes. Electrolytes are the solutions which contains ions, and these ions can conduct electricity. Okay, so first we'll talk about the electrical conductance and ionic conductance. Important terms and formulae, variation of conductivity and molar conductivity, and Kohlrausch law. Okay. Next is your first one, electrical conductance. It is the nature of the electrolyte added, and the size of it depends on the nature of the electrolyte added. Then it depends on the size of the ions that is produced. Bigger size means less conductivity will be there. Nature of the solvent and its viscosity. If the solvent is too viscous, then the electrolytes cannot flow and the conductivity will decrease. It depends on the concentration of the electrolyte. More is the electrolyte, more ions, more conductivity will be there. It depends on temperature. If temperature increases, molar conductivity also increases. Now if I talk about metallic conductance, or just a minute, this is, sorry, I have slightly made a small mistake, let me just change it. This is your metallic conductance, okay, or you can say electrical conductance, and this is actually your ionic conductance due to the ions. Here the conductance is due to electrons. So next we have here, it depends on the nature and the structure of the metal, very important. Next, depends on the number of valence electrons per atom. If more number of valence electrons are there, then it will conduct more. Temperature, it decreases with the increase in temperature. When in metal conductors the temperature increases, the friction also increases, so that is why the conduction decreases. Okay, now we will see about some important terms, their formulae and their units. Okay, so first let's talk about resistivity. Its symbol is given as rho. Now, okay, first let's talk about resistance here. Its symbol is capital R. It is something which opposes the flow of current. Here the unit is ohm and the symbol is omega. Resistivity is denoted by rho. It is the resistivity for a substance is its resistance when 1 meter long and its cross-sectional area is 1 meter square. So you have ohm meter or ohm centimeter as its units. Next we have conductance. Its symbol is Z and the definition here is inverse of resistance, and here it is ohm inverse or S or Siemens. Coming to conductivity, it is denoted by kappa. Conduction by electrolyte per unit volume, and here the I can say the symbol is ohm inverse, meter inverse, or S meter inverse, or S centimeter inverse. Next we have cell constant. It is denoted by G star. The formula I'll also show you. It is written by L by A, length by area. So its unit is meter inverse or centimeter inverse. Molar conductance, it is the conductance of all the ions produced by 1 mole of an electrolyte. Its unit is S centimeter square mole inverse or S meter square mole inverse. Clear? Okay, now let's talk about the important terms and definitions. Okay, so first of all, resistance formula, R is equal to rho L by A, and then resistivity, you can just inverse it, so we will get R A by L. Cell constant is G star, denoted by L by A. Conductance is inverse of resistance, so 1 by R. Conductivity, kappa, okay, it is 1 by R into L by A, and its unit is S centimeter inverse. One second, you can see 1 by R is ohm inverse, which can be written as S, and L by A can be written as centimeter inverse. Then we have molar conductivity, which is kappa into 1000 by C, and the unit here is S centimeter square mole inverse. Okay, now let's talk about the variation of conductivity and molar conductivity. Okay, so now see, first conductivity, that is kappa. So what is conductivity is, it is the conductivity of all the ions present in one unit volume. Okay, so for example, if you have a solution like this, if you have an electrolyte like this, and these are like, suppose I'm just dividing it like this, and this is 1 unit of volume. Okay, so whatever ions are present here, okay, suppose there are 5 ions. So whatever is the conductivity because of the ions present in 1 unit volume, that is called as the kappa or conductivity. Now what happens when you dilute it? Okay, when you add more water. Now suppose what will happen, I'll add some more water here. So I have diluted it. So now there is more water, and you can see what will happen. The ions which were present earlier 5 here will now get distributed. Okay, now there will be only 3 ions here because there is now more solution, more solvent, so the ions will start flowing and the number of ions per unit volume decreases. If the number of ions per unit volume decreases, then the conductivity will also decrease, right? So that is what we will understand now. I'll just erase and explain this one. See here. Yes, conductivity always decreases with a decrease in concentration both for strong and weak electrolyte. This may be explained by the fact that the number of ions per unit volume that carry the current in a solution decreases on dilution. So when you dilute it, the number of ions per unit volume decreases, and as a result of which the conductivity also decreases. Now let's talk about molar conductivity. Okay, what is molar conductivity? It is the conductivity due to the ions present from 1 mole of an electrolyte. Okay, so you can see here what happens for weak electrolytes and for strong electrolytes. So basically, first of all, molar conductivity increases, okay, both for strong and weak electrolyte. But we will observe the difference and what is the rate of increase. So lambda m for weak electrolytes increases more due to the increase in the dissociation of the ions. Now what do you mean by weak electrolytes? Weak electrolytes are those which cannot dissociate completely or which has less number of ions. Now when you dilute it, its dissociation increases. Okay, what happens when you dilute it? The dissociation increases and the number of ions produced, that also increases. Now if the number of ions increases, dissociation increases, the current carrying will also, the conductivity will also increase. So in case of weak electrolytes, the increase is much more. Okay, but in case of strong electrolytes, what happens? There is increase definitely, but the increase is less. Okay, like for example, see, suppose weak electrolyte is there and strong electrolyte is there. Weak electrolyte generally has less conductivity as compared to strong electrolyte. So for example, weak electrolyte conductivity was 5 and strong electrolyte conductivity was suppose 40. Okay, I'm just giving an example. Now you diluted it. So weak will become from 5 to 20. Okay, but 40 will become from 40 to 42. You see the rate in increase. Here how much increase has happened? A tremendous increase has happened because dissociation increased and number of ions also increased. But in strong electrolyte, the increase is only due to the increase in the mobility of ions. What do you mean by mobility of ions? So let us consider, for example, NaCl is a strong electrolyte. What are the ions here? Na plus and Cl minus. They are oppositely charged, so they both are strongly attracted towards each other. So as a result of which they are not able to move freely because they are attracted towards each other. Now what you do, you add water, you dilute this one. Then what will happen? Na plus will be thrown here, Cl minus will go somewhere else. So their mobility will increase because their attraction force is decreased and now they can move freely in a faster way, and that is the reason why the conductivity, molar conductivity increases for case of strong electrolytes, but the number of ions remains still the same. So if you compare, the increase in weak electrolyte is more as compared to the increase in the strong electrolyte. Okay. Now there is an equation which gives the relation between molar conductivity and concentration, that is lambda m is equal to lambda naught m minus a root over of c. This equation is called as d by Huckel-Onsager equation. Okay, d by Huckel-Onsager equation. Okay, now based on this we will draw graph also. Now A is same for same type of electrolyte. Okay, same type of electrolyte means suppose I have two electrolyte NaCl, okay, and KCl. If the cation charges are same and if the anion charges are same, then it is called a same type of electrolyte. For example, if you have MgCl2 and some other like NaOH, okay, you see this is plus 2, this is minus 1, and this is plus 1 and this is minus 1. The anions charge are same but cation charges are not same. So that means this is not the same type of electrolytes. Okay. Now let's move to the graph here. You can see the graph variation of molar conductivity. Sorry, this shape will be lambda m. Okay. You can see that for this is a strong electrolyte. The initial conductivity was somewhere here. Okay. When the concentration was higher, the value was here, and when the concentration decreased, the value somewhere came here. Right. This is the increase in molar conductivity. Now for the other one, if you see, okay, this is the value of molar conductivity earlier when the concentration was higher, but when the concentration decreased, this is the value of molar conductivity. So from somewhere near here to here, the value has increased so much. You can see the increase in value for weak electrolyte and the increase in value for strong electrolyte. Okay. So this is important graph and it is asked in the exam, so prepare it thoroughly. Now we will talk about one law called as Kohlrausch law. So what is Kohlrausch law? So before that, let us understand limiting molar conductivity. So we just now saw that when the concentration decreases, molar conductivity increases, right? But when you decrease the concentration to the maximum, okay, you keep on decreasing and you reach the maximum value of molar conductivity, okay? After that, there is no change in the molar conductivity even if you decrease the concentration. So when concentration almost approaches zero, the molar conductivity is known as the limiting molar conductivity and it is denoted by lambda naught m. Okay, now let's talk about Kohlrausch law. So what is Kohlrausch? That is very simple thing. Limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and the cation of the electrolyte. Means suppose if I am talking about the limiting molar conductivity of NaCl, that is due to the molar conductivity of Na plus and due to the molar conductivity of Cl minus. That is quite obvious, right? NaCl as a whole is a electrolyte because of Na plus and Cl minus. So what the total molar conductivity of NaCl will depend on the molar conductivity of Na plus and Cl minus. So this is schematically represent like this. So if you have, for example, AlCl3, that will give you the molar conductivity of Al3 plus and 3 times of Cl minus, right? Okay, next we will see here to calculate alpha. So what are some applications of Kohlrausch law? So alpha value is lambda m by lambda naught m, where lambda m is your molar conductivity. Okay, lambda m is molar conductivity and lambda naught m is the limiting molar conductivity. Okay, limiting molar conductivity. Clear? So here lambda m is equal to kappa into 1000 by C. Okay. Now Ka value is equal to C alpha square by 1 minus alpha. K is equal to C alpha square by 1 minus alpha. And now if I substitute this alpha as lambda m and lambda naught m, then I'll get an equation like this. So you can directly calculate alpha separately and can substitute here. So we can also, it is used to calculate the acid dissociation constant value. Okay. Next is to find the lambda naught m for weak electrolytes. So if you see the graph for weak electrolytes, what we have observed is, let me just go back, you can see that for strong electrolytes, if you extrapolate the graph, you can find the limiting molar conductivity. But for weak electrolyte, it is not possible through the graph because we cannot extrapolate it. So we can indirectly find the limiting molar conductivity of weak electrolytes using the Kohlrausch law. Okay, so I'll give you one example. Suppose I want to calculate the limiting molar conductivity of one weak electrolyte like HCOO Na. Okay, I want to find for this one. Okay, now what values, I cannot find it directly, or let me just take HCOOH, that is a weaker electrolyte. So if I want to calculate for HCOOH, okay, and what are the values given to me? I have been given with HCOO Na value is given to me, okay, and I have been given with HCl value, and I have been given with NaCl value. Okay, so these three values are given to me and I have to find for this one. So see, this one I can write it as HCOO minus plus Na plus, right, cation plus anion. Similarly, this I can write as H plus and Cl minus. Okay, then this I can write as Na plus and Cl minus. Right, now what will happen if I add this one? Okay, this all values I will add. See, if I add this one and this one, then I will get these two. Okay, when I add these two, there is extra NaCl is formed and I can subtract this value. So suppose I'm writing this as 1, 2 and 3. So if I add 1 plus 2 minus 3, then I will get the value here, that which is remaining with me will be HCOO minus plus H plus. Okay, so that will be my final equation, and that is how I calculate the lambda naught m for weak electrolytes. Okay, now let's talk about the electrolysis and electrolytic cell. So first of all, we'll understand what is electrolytic cell, what is Faraday's law, and then products of electrolysis. Okay, so what is electrolytic cell here? See, we have understood what is galvanic cell. Electrolytic cell is just the opposite of that, right? So in an electrolytic cell, an external voltage or source is provided due to which a non-spontaneous chemical reaction takes place. Means here electrical energy is converted to chemical energy. These processes are widely used in laboratories and chemical industries. So we'll see some application of this electrolysis first. So the first application is in the purification of copper. Okay, so what happens here? The impure copper is used as anode and the pure copper is used as cathode. Okay, you have an impure copper as anode and you have the pure copper as the cathode. Okay, this is the impure one. So now what will happen when you connect it with an electrolyte? So this will undergo what? Oxidation, the anode one. So copper 2 plus will come out from here and then they will go and deposit here, right? It will get reduced here. So all the like from this impure rod, all the pure copper will come out and will get deposited here, and finally the purification of copper takes place. So impure copper dissolves at the anode and get deposited at the cathode. This process produces high purity copper for industrial use. Next, there are some other uses also. Production of metals by electrolysis. So if you have studied the extraction process in class 10th, that is metal extraction, their electrolysis was used to get pure metals, right? So metals like sodium, magnesium, aluminium are produced by electrochemical reduction of their cations. So these metals cannot be reduced chemically, so electrolysis essential. So you can see sodium and magnesium are produced by the electrolysis of their fused chlorides. Similarly, aluminium is produced by the electrolysis of the aluminium oxide in the presence of Na3Al(F6). Okay, so here what happens? Sodium gets reduced like this, Na plus 1 electron, and you get pure sodium. Similarly, you get magnesium gets reduced to give you pure magnesium. Okay, and here aluminium plus 3 gets 3 electrons to form pure aluminium. Okay. Next is we'll talk about Faraday's law. So we have two types of Faraday's law, Faraday's first law and Faraday's second law. Okay. So what is Faraday's first law? Faraday's first law states that the amount of chemical reaction which occurs at the electrode during the electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte. So if you have a, I'll say a electrochemical cell or an electrolytic cell, in that the chemical reaction that is happening, that is proportional to the amount of current that you have produced. Okay, if you have given more current, more reaction will take place. If you have given less current, then less reaction will take place. So you can see here formula of this one, M is equal to ZIT, where I stands for your current. Okay, I is current in amperes and T is time in seconds. And Z is what? Electrochemical equivalent, and Z is equal to molar mass divided by N into 96500. Okay. Now we will talk about Faraday's second law. The amount of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to the chemical equivalent weights. Okay. That means suppose I have two solutions like this. Okay. You have one cell like this, you have another cell like this. Okay, then this one will get deposited here and this one suppose will get deposited here. So the amount, you are passing same amount of current for both the cells, then the amount of mass deposited here and the amount of mass deposited here, their ratio will be equal to their equivalent weights, means m1 by m2 equal to e1 by e2. What does E stands for here? It stands for equivalent weight. And how do we calculate equivalent weight? That is equal to molar mass by n factor. Okay, n factor is the valency or the number. Based on the structure, we have different n factors. Next, we'll talk about the products of electrolysis. This is very, very important. You should be knowing the products. So for molten NaCl, sodium metal will be produced at cathode, whereas because it is positively charged, so it will move towards the negative electrode, and chlorine gas will be produced at anode. For aqueous NaCl, hydrogen gas will be produced at cathode and chlorine gas will be produced at anode. Now we'll talk about dilute H2SO4. Here hydrogen gas is produced at cathode, oxygen gas is produced at anode, and for concentrated H2SO4, hydrogen gas is produced at cathode, but S2O8 2- is produced at anode. Okay. Next, we'll talk about batteries. So we have two types of batteries. One is your primary battery and the other one is secondary battery. Primary batteries are those batteries which can be used only once. Okay, means that if the reaction is over, the battery is of no use after that. But secondary batteries are those which can be used again and again, means these batteries can be actually recharged by passing current through it in the opposite direction. Okay, so you know mobile batteries, we recharge it again and again, but some pencil batteries come, we just throw it. Remote batteries, we generally throw it after one time use. So primary and secondary battery. Example, if you see, for primary battery we have dry cell and mercury cell. For secondary batteries we have lead cell and nickel cadmium cell. Okay, so now we will see these batteries reactions. So for dry cell, that is your dry cell, here we have zinc at the anode and MnO2 is used in the cathode position. And yes, you should know these reactions, so you have to remember it. Mercury cell, again zinc is used as anode and mercury oxide is used in the cathode. Now coming to lead storage cell, here this reaction is also important. This one you should remember. Lead is oxidized to lead 2 plus in the anode and lead plus 4 is reduced to plus 2 in the cathode. Okay, nickel cadmium cell, here cadmium is there and nickel oxide is there. Okay. Now we'll talk about fuel cells. So what are fuel cells? So till now we have studied that the chemical reactions are converted to electrical energy, right? And what type of chemical reactions, which type of reactions? Redox reactions, right? Similarly, the fuel cells are due to the combustion of the fuels. So galvanic cells that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. directly into the electrical energy are called as fuel cells. Okay, one of the most successful fuel cells that we have studied so far is the hydrogen oxygen fuel cell. In this, what happens, hydrogen and oxygen are bubbled. You can see hydrogen and oxygen are bubbled through porous carbon electrodes into concentrated aqueous NaOH solution. Catalysts like finely divided platinum or palladium metal are incorporated into the electrodes for increasing the rate of the electrode reactions. Okay, so you can see here this is the reaction of fuel cell, and you can write down the equation also. Cathode O2 plus 2 H2O plus 4 electron gives you 4 OH minus, and for anode we have H2 plus 4 OH minus gives you 4 H2O plus 4 electron, and the overall reaction is 2 H2 plus O2 gives 2 H2O. Okay. Now we'll talk about corrosion. So corrosion is a very common phenomenon of oxidation of metals to which leads to a lot of destruction, and a very famous corrosion example is rusting, where we are talking about the corrosion of iron. Okay, so basically the corrosion is a reduction, is a I can say redox reaction. Okay, so we'll understand how it is an electrochemical phenomenon. So exactly what happens, iron from one of the part, okay, it gets oxidized and gives you Fe2 plus, okay, and these Fe2 plus moves outside, whereas these two electrons move to some other place of the iron metal, and it is used to reduce this oxygen to water. Okay, you can see the reaction here. Fe undergoes oxidation to give you Fe2 plus and 2 electron, whereas oxygen gains electron to give you water molecule. Then atmospheric oxidation, what happens, Fe2 plus, you can just then this Fe2 plus which is produced here, they are further oxidized in presence of oxygen to give you Fe3 plus or oxides of iron, okay, or other I can say hydrates of iron oxide, which leads to corrosion. Clear? Okay, so children, this was the overall summary of this chapter, overall one-shot revision of the chapter, and I hope that this video was helpful. If you didn't understand anything, let me know in the comment section. But yes, this chapter is very important, so please like watch 1 or 2 times and understand each and every concept. Still, if you have doubt, do not hesitate, you can put down in the comment section. Thank you so much for watching. All the best, and please remember we have very few days left, so let's buckle up and let's put all our 100% of efforts in every day. Thank you so much. Bye bye. Take care.